Now, like the beginning of the last video, I'm going to start off with a proof. And the proof to find the derivative log function is really quite simple. So we know that the natural log is the inverse of the natural exponential function, which means that if we have something like e log x, that's going to be equal to x. Now, we don't know the derivative of log x. Right? That's what we're going to try and find. And to find it, I'm going to do something maybe a little counterintuitive. I'm going to replace log of x with the general form. So this is conceptual. This requires a fairly high level of conceptual thinking, abstract thinking, right? And I'm going to do this. Now, it's important that you develop your abstract thinking and your conceptual thinking, because that's what you're going to need to be a successful economics major and really understand economic theory, and then also be able to estimate it statistically in practice later. Now, I'm going to take the derivative of this thing, and I'm going to take the derivative of, I'm going to take the derivative of both sides. So I'm going to take the derivative of this thing with respect to x. And what I'm going to get is I'm going to get e gx, that's the exponent rule, multiplied by g prime of x, that's the chain rule, right? I'm applying the chain rule, so I'm taking the derivative of the outside function, which is the natural exponent, multiplied by the derivative of the inside or interior or kernel function. And this whole thing is going to be equal to 1. Now, I'm going to replace g of x equal to the log of x. And so I've got e to the log x multiplied by g prime x is equal to 1. These two are inverses, and so we're just going to be left with x times g prime x is equal to 1, and g prime x, that's the derivative of the original gx function, is going to be equal to 1 over x. And finally, what do we get? We get the derivative of log x over x is equal to 1 over x. Now there's our answer. So I'll write over here, if f of x is equal to log of x, this implies f prime of x is equal to 1 over x. So if I've got something like the log of x plus 1, and I want to find dg with respect to dx, it's going to be equal 1 over x plus 1. So whatever is in this bracket is going to move into the denominator, and we're going to get 1 over x plus 1. Let's work through some practice problems together. So we'll do f of x first. And 4 is just a multiplicative constant. And so if I want to find f prime of x, I'm going to take everything inside this natural log bracket right in here. And what am I also going to do? I also have to use the chain rule. So notice how we're using the chain rule all the time. As soon as we learn, once we learn the chain rule, we're always using the chain rule. Chain rule is very important. And what's the derivative of the inside? Well, this is just an additive constant. It's just going to disappear. I've got negative 2x to negative 2 minus 1. And so the derivative of this thing is going to be equal to negative 2x to the negative 3 over x2 plus 1. And I guess I could simplify this if I wanted to by getting rid of the negative exponent, like so. Okay. Now why don't you try the next one? Press pause, work on it yourself, and then we can go through the answer together. Now looking at this question, it looks like we're going to have to use what? We're going to have to use the product rule. We've got the product rule. We've got, one function here and one function there. Well, we won't bother naming them. Now, we want to find the derivative of g. Oh, it looks like we've got a z in here. I guess, well, let's just let that be an x. I'll fix that on the slides. G prime x is going to be equal to the derivative of this thing here. Well, that's just 1 multiplied by log of 2x. And I'm going to make sure I have enough room to work with here. In fact, maybe I will just take off some of this over here. And that's our first, the derivative of the first product multiplied by the second function, plus 2 plus x, that's just this thing, times, using the log rule, what have we got? We've got 1 over 2x. And, there's just really not very much that I can do with this thing in terms of simplifying. So I think we just have to leave it right there. And a student pointed out to me that I forgot this 4 up here, so I'll go back and you could have just factored out, could have the 4 out over here, the 4 here, and then there's a 4 here. And so we're going to have negative 8 over x plus 1 x cubed. So here is the log function. This is what it looks like. Let's summarize very briefly some of the properties of the natural log function. And so we can say that it's, well, 1, it is differentiable. So we can find a derivative. We just did that together. 2, it's strictly increasing, right? If x gets larger, y also gets larger. Not as big as the change in x, but it is getting larger. 3, what shape is this? Well, it's concave. F double prime is going to be less than 0. So the function is increasing, but it's increasing at a decreasing rate. And just to remind you, we saw that was just equal to x if, we could write that would be equal to x2. If we have the log of xy, that's equal to log x plus log y. And if we have the log of x squared, that's equal to 2 log x. And we can go whichever way we wish. So if we had something more abstract like rho log x, that would be equal to the log of x rho. Something else for log x is undefined if x is less than 0. As x approaches 0, log x approaches negative infinity. This last one might seem a little weird, but this is going forever down there, and we say it asymptotically approaches, well, I shouldn't say that, it just gets smaller and smaller. And finally, 6, as x approaches infinity, as x gets really, really large, log x also approaches infinity. So if you want to think outside of numbers and some just gigantically huge number, if x is a really huge number, then log of x is going to be some huge number too. The log of a huge number is also huge. And so that was sort of encapsulated here. It's just very similar to the idea of strictly increasing. So it's always getting bigger and bigger. There's no maximum on that function. And of course, you've seen a lot of these before, and you've been looking at these for the past, or at least certainly a few weeks ago when we introduced the subject of logs. So this is just really a review and remind you what they're all about.